Welcome. We're going to start chapter 19, temperature, and then I'll cover the temperature scales of the Fahrenheit and the Kelvin. In this chapter, we'll be introduced to the temperature scales. We'll do some examples of that, and then we'll be introduced to length expansion and length contraction of a metal and volume expansion of a liquid, right? And then we'll also be introduced to the ideal gas law, PV is equal to nRT or nKT. So this is an introduction to the whole topic of thermodynamics. And then in the next chapter, we'll delve more into it in chapter 20, and then chapter 21, and chapter 22. So there's going to be about 4 chapters of thermodynamics that we will cover. So we are introduced to the temperature scale here. The Fahrenheit scale is 9/5 Celsius plus 32, and the Kelvin scale is Celsius plus 273.15. So we can give some common temperatures. The temperature for which water boils is 100 Celsius. And in the Fahrenheit scale, it is equal to 212 Fahrenheit. And in the Kelvin scale, it'll just be 100 plus 273, 373.15 Kelvin, right? And then water freezes at 0 degrees Celsius. So that will be equal to 32 Fahrenheit. And then that will be equal to 273.15 Kelvin. Okay, the scientific usage of the temperature scale is always in the Kelvin, because the issue with the Celsius, there's a couple issues, is that you actually have something known as negative Celsius, right? You can go below 0 Celsius. The definition of temperature is that it is the measure of the average kinetic energy of molecules. This is something we will cover in the next chapter, chapter 20 and 21. And we'll see that temperature measures kinetic energy. Well, if kinetic energy is always positive, temperature has to always be positive, right? So it doesn't really make sense that you have something that is negative temperature, because you can't have negative energy. You can't have negative kinetic energy, right? The other reason that Celsius is not good is that it is kind of arbitrary. 0 Celsius is set at the temperature that water freezes on Earth, right? But if you go to a different planet, on Mars or Jupiter or Venus, right, water will freeze at a different temperature. So are we going to now make a new scale for Celsius for a different planet, right? The Kelvin scale is set so that everybody in the universe will always agree for the same Kelvin scale. 0 Kelvin is the temperature at which all molecular motion stops, all random molecular motion. All random molecular motion stops. Well, everybody in the universe will agree that no matter where you go, 0 Kelvin will be 0 Kelvin. All molecular motion will stop at 0 Kelvin. Now on Earth, 0 Kelvin is equal to negative 273 Celsius, right? 0 Kelvin is equal to negative 273 Celsius. But if you were on a different planet and water froze at a different temperature, then 0 Kelvin would equal some other kind of Celsius, maybe negative 300 Celsius, negative 400 Celsius, right? So the Celsius can change depending on what planet you're on, but the Kelvin will never change, right? The other thing that we see from here is that a unit change in Fahrenheit is equal to 9/5 times unit change of Celsius, right? So if you go from 20 Celsius to 21 Celsius, you've basically gone up by 1 Celsius, right? Delta C is equal to 1 Celsius. Well, whatever Fahrenheit the 20 is, we can calculate what that is, and wherever Fahrenheit 21 is, the delta F is going to be what? It's going to be 9/5, so it's going to be 9/5 times 1 Celsius. So it's going to be 1.8 Fahrenheit, right? So a unit change in Celsius of 1 yields a unit change of Fahrenheit that is almost 2. So the Fahrenheit goes up quicker and goes down quicker, right? Fahrenheit. Well, if you subtract them, what should you get? 1.8 Fahrenheit, which is exactly what we said. A unit change of Celsius yields same as a unit change of Fahrenheit. How about a unit change in Celsius versus a Kelvin? Right? If I do the delta K, delta C, well, they're actually equal. So any unit change of Celsius will also equal a unit change of Kelvin. Well, what does that mean? Any equation that we have from now on that relies in the change in temperature of something, and we're going to be introduced to that later in this chapter. Change in length is alpha, L initial, change in temperature, right? This is the change in length of a metal. If you heat the metal by a certain amount, delta T, right, the metal will increase its length by a certain amount, right? Well, any change in temperature in Celsius is also equal to the change in temperature in Kelvin. Therefore, we do not have to change temperature to Kelvin for these kinds of equations that rely on the change in temperature, right? Then there are some equations that rely on the temperature, not the change in temperature, such as the ideal gas law. So the ideal gas law is saying the pressure of a gas times the volume of a gas is equal to number of moles times gas constant times the temperature. But the absolute temperature, right? So when the temperature is 0 Kelvin, if the container of gas has 0 Kelvin, what's going to happen? Then the pressure times the volume is going to be 0. That means the pressure is going to be 0 of that gas. The molecular motion stops, right? Could we use Celsius in this case? If I put here negative 273 Celsius into here, would that work? No, because that would mean the pressure is negative. So definitely it doesn't work. So any equation that relies on the temperature must use Kelvin. Change in temperature can use Celsius or Kelvin. The temperature that is of importance that we can use is the normal body temperature for a human. So body temperature is going to be 37 Celsius, which is going to be 310 Kelvin, right? And then in Fahrenheit, what is that going to be? Well, we can put 37 Celsius into here, right? So that's a good body temperature, and if you are a little bit over that, then you have fever, right? And then another temperature we can say is like comfortable room temperature, maybe a little bit warmer than 20. We can say 25 to 27. So room temperature is going to be around 25 to 27 Celsius. Okay, what is that going to be? Well, if you add 25 to 273, you're going to get 298. 298 to 300. So 298 to 300 Kelvin. So just remember as a ballpark that 300 Kelvin is the approximate temperature for a comfortable room temperature, right? And then 310 is the body temperature. So usually our body temperature will be warmer than a typical room temperature, okay? So now we can do some examples based on this. Thank you very much.